In this lecture, we will see the controller tuning for a second order plant using a proportional controller. So P controller, in the P controller, D of S is Kp and the plant transfer function is some K divided by S plus sigma whole square plus omega n square. I hope it's omega n square. Oh, sorry, S plus sigma whole square plus omega d square. Yeah, omega d whole square. This is the plant, second order plant. So first is the stability. For stability, let's check what is d of s into g of s. That is kkp divided by s plus sigma whole square plus omega n square. So for stable, and also g equivalent of s will be d into g by 1 plus gd. So k into kp divided by here it will be kkp plus omega n square plus s plus sigma whole square. So for a proportional integral controller, the closed loop transfer function is also second order system. So it will be, let's write it as k dash by s plus sigma whole square plus omega d dash square, like this we'll write. So actually here it should be omega d, not omega n. Omega d square into omega d dash square, where you know what is k dash. K dash is kkp and omega d dash is omega n square plus kkp. And omega d dash square will be omega n square plus kkp. Okay, so this is the stability. For stability, what is the criteria? The real part should be positive, which means that here the pole is at what? S plus sigma whole square plus omega d dash square will be 0. So s plus sigma square equals to minus omega d dash square, s plus sigma is to plus minus j omega d dash. So s will be minus sigma plus minus j omega d dash. The pole will be placed at this point. So this will be the placement of the pole. So one condition is that sigma should be greater than 0, which means zeta into omega n should be greater than 0. This is first equation. So this is for stability. Then for steady state error, first we'll find the DC gain. DC gain is limit s tends to 0 g of s into d of s. What will be that? That will be, I'll directly write kkp by sigma square plus omega n square. This is the DC gain. So what will be steady state error? It will be 1 by 1 plus kdc, that is kkp by sigma square plus omega n square, which is sigma square plus omega n square divided by kkp plus sigma square plus omega n square. This will be the steady state error. So here there is no as such an identity which is used to tune the KKP, but this is, only KP because it's a P controller. But this is just to show that key only for proportion. So for a proportional controller, this is how it is. Yeah. So stability is done, steady state error is done. Now comes the transients. For transients, again, for a second order system, you know that the rise time is 1.8 by omega n, and the settling time is 4.6 by sigma or zeta omega n. So our settling time or rise time should be less than equals to their specified time. Similarly, our settling time should be less than equals to the specified. So Ts and Tr are given. So then we'll find the relation of omega n and zeta omega n. So let's write zeta into omega n as sigma, and what we'll get is omega n will be what? If you do the reciprocal, the identity will reverse. So omega n will be less than equals to 1.8 by Tr, and sigma will be less than equals to 4.6 divided by Ts. So omega n is less than equals to this thing means, so here this identity omega n, which is less than equals to 1.8 by Tr, it represents a circle with maximum radius. Let's say this is equation number 2. Then sigma less than equals to 4.6 by Ts, this represents the maximum what? Real part of the S term. This is equation number 3. One last transient is remaining, that is overshoot. Overshoot is what? The expression of overshoot is exponential of minus pi zeta by under root of 1 minus zeta square. And zeta is a function of theta, which you already saw. Quickly I'll just write here. Let's say this is sigma, this is omega d, then this becomes omega n, this is theta. So we write we know omega d equals to omega n under root of 1 minus zeta square, or omega d by omega n is under root of 1 minus zeta square, which is also equals to what? Sin theta. Like this we can write opposite by hypotenuse. So therefore we can write zeta in terms of theta, and first here we'll find zeta. So here it means that our this term minus pi zeta divided by under root of 1 minus zeta square, this is the expression of our peak overshoot, should be less than equals to the specified peak overshoot, right? Just like for rise time and settling time. So similarly, if we do ln on both the sides, it will be minus pi zeta by under root of 1 minus zeta square less than equals to ln of mp, ln of mp. So then it becomes minus pi or if we square it, it will be pi square zeta square by 1 minus zeta square less than equals to ln of mp whole square. So if we just write 0 greater than equals to it will be 1 minus zeta square into ln of mp square, like this we'll do minus pi square zeta square on solving it. So it will be, if we take zeta square common, what will it be? It will be minus ln of mp square minus pi square, then into plus ln of mp whole square should be greater than equals to 0. Like this it will be. If you multiply on negative sign, sign will be reversed. So zeta square into pi square plus ln of mp square minus ln of mp whole square should be greater than equals to 0. So it's a quadratic. So if we solve it, it becomes zeta square greater than equals to ln of mp whole square by pi square plus ln of mp square. So zeta will be greater than equals to plus minus ln of mp divided by under root of pi square plus ln of mp whole square. This will be, oh, I did not reverse the sign. The sign should be reversed here. Less than equals to, less than equals to, less than equals to. So it means minus ln of mp by under root of pi square plus ln of mp whole square less than equals to zeta less than equals to this ln of mp by under root of pi square plus ln of mp whole square. So if you know zeta, we can find theta. Under root of 1 minus zeta square, that is sin theta. So basically we have, by using sin theta equals to under root of 1 minus zeta square, we get that theta should be equals to minus theta max to theta max. So basically this is another identity, equation number 4. Where theta max, what is theta max? Theta is what? Sin inverse, yeah, under root of 1 minus zeta square, which will be one minus ln of mp whole square by pi square plus ln of mp whole square. So it will be sin inverse of pi square will be there, so plus minus pi by under root of pi square plus ln of mp whole square theta max. Basically if you're writing plus minus theta max, then there is no need to give here plus minus sign. So this will be the theta max. So by doing 1 intersection 2 intersection 3 intersection 4, what we get is, how to find kp is using this equation. What does equation number 1 said? Sigma greater than 0, and yeah, sigma greater than 0. And what does equation number 3 says? Sigma greater than, where is equation number 3? Yeah, sigma is less than 4.6 by ts. This is 4.6 by ts. So it has to be less than this. Less than or greater than? Question number 3. Yeah, less than equals to 4.6 by ts. And this is equation number 1. This is equation number 3. So, and equation number 2 is for the radius. Yeah. So we'll draw a circle with the radius of 4. Equation number 4 we'll use, no 2. 1.8 by tr, this is 1.8 by tr, this radius, so it has to be inside the circle. This is by equation number 2. And equation 4 says that theta is between theta max and theta minimum. Okay, theta max, theta minimum, but theta should be on the left hand side or right hand side of axis, that we'll just quickly see. So as I said, using the proportional controller, the second order system remains the second order system only. So basically it will be on the left hand side of the, its real part will be on the left hand side of the axis. So basically it will be on the left hand side. This will be theta max and this will be theta min, means minus theta max. This will be minus theta max. So between theta max and theta min, this is equation number 4. This is sigma axis and this is j omega axis. So where is the intersection, the common point of it? It is here. This is the point of operation. Not point of operation, the region of convergence or region of stability or region of what do you say, controller design. So our controller has to be designed in such a way that the complex axis lies in this part only. Then it will satisfy all the conditions: stability, steady state, and dynamic responses. So then comes how to find Kp. So what is the ultimate aim? That theta lies between theta max, theta min, sigma. So equation 1 is about sigma. Sigma is zeta omega n. So we know the relation. Actually, if sigma is positive, actually sigma is always positive. But our as per our second order system, which is G equivalent of S. Here we saw G equivalent of S in this. Yeah, this is G equivalent of S. So S is minus sigma plus j omega. So whatever is the sigma, it will be on the left hand side of the axis. So basically this thing, our 4.6 by Ts has to be projected toward the negative side. So basically this will be our minus 4.6 by Ts. This will be minus 4.6 by Ts. Sigma equals to minus 4.6 by Ts. Then our region of operation becomes this. And our identity says that it should be less than this. Our region of operation becomes enhances and it becomes up to here. This will be the new area of or basically the region of controller design. So I'll write here minus 4.6 by Ts less than sigma is less than 0. Sigma should be in this range and sigma equals to zeta into omega n. Okay, this is one condition. Equation 1 3 satisfied. 2 is this omega n less than equals to 1.8 by tr. 1, 2, 3 and then equation 4 is of theta, or basically we'll write zeta. This we'll call as zeta max. This is the zeta max. So minus zeta max less than equals to zeta less than equals to zeta max. This is the identity. So we can find zeta from this relation. Minus zeta max less than equals to zeta less than equals to zeta max. So by fixing a zeta and fixing omega n, we can find sigma. Okay, so basically zeta will fix, and these are the maximum range of variation of zeta, that is ln of mp by under root of pi square plus ln of mp square. So mp is known to us. So what is known? tr, ts, mp, and steady state error is known to us. Steady state error is what? ESS is this. Where is the equation? Yeah, sigma square plus omega n square by this, which is known to us, which should be between 2% or this percent of limit. So using this we can find omega d and kkp. So a steady state error is given to us. Okay, using this 2% limit and all, we can find the steady state response. So basically steady state error gives the significance of ESS for a peak control. Now here the time response will be like this. This will be the steady state value, and this is how the response will be. So this difference is called as the steady state error. Rise time, peak time, everything is there. This will be overshoot. This is the steady state value. This should be y star, and this is y of t, and this is t. Rise time and all, you know. So basically this will be 0.9 of t, this will be 0.1 of t. So basically 0.1 of y star and 0.9 of y star. So this will be rise time, and this will be settling time somewhere here. So basically this will be the case of the P controller for a second order system. There will be some steady state error. Now we know what is ESS. ESS is known, which is based on 2% band. So using the expression of ESS we can find Kp, because in all the expression here what we have to find is Kp, but what we are getting is, we'll solve this and we'll get zeta. From zeta means first we have to assume zeta max, zeta mean, then we'll get to assume omega n, then based on zeta and omega n we'll find sigma. But our ultimate aim is to find what is Kp, what is the range of Kp. So whatever is the ESS known to us should be less than equals to greater than equals to our found ESS, which is as per this equation. Where is the equation? Yeah, this one. This. So using this we can find Kp. K is known to us. What is known to us? K is known because the plant is known. K is known and sigma is known. Okay, because K by S plus sigma whole square plus omega n square. So basically omega n is known to us. What we have to find is K. So basically sigma is known. So using this equation we can find Kp. Easily we can find Kp. So this is the range on the Kp. So using this we can tune the controller using the time domain analysis. In the last lecture we have seen the tuning of PI controller using a using a second order plant. So actually there was a slight mistake here. So what we saw here is that, yeah, so basically I'll rectify that mistake here. So let's see what is in the case of PI controller. So I'll again write it, and we'll just modify it based on the what thing we do. So basically D of S will be what? Kp plus Ki by S, or SKP plus Ki by S, or it will be Kp by S into S plus Ki by Kp. This is the preferable form. Then stability. What will be D of S into G of S? G of S will be K by S plus sigma whole square plus omega D square. It will be Kp into S plus Ki by Kp divided by S into S plus sigma whole square plus omega D square. So basically, naturally, this is the D of S into G of S. Now the closed loop response G equivalent of S will be G into D by 1 plus GD, which is Kp into S plus Ki by Kp, and here it will be S into S plus sigma whole square plus omega D square plus Kp into S plus Ki by Kp. Now here there is no assumption, just like what we did in the first order system, that is A equals to Ki by Kp. Like that, there is no assumption as such in this thing. So let's keep it generalized. So here it will be a third order plant or third order system. So a first order system is nothing but S equals to minus sigma. A second order system will be S equals to minus sigma plus minus J omega D. So a third order system will be in a, so basically it's in a single coordinate like this, sigma. Here it will be, this will be sigma, this will be J omega D. What will be the third order system? It will be in a 3D, sigma, and here it will be J omega D, and there will be one more coordinate as Z hat. So here it was a linear curve. Here S equals to 0, it was a linear curve, means just a plane. S equals to sigma plus J omega is nothing but a complex vector in this direction, and if you just compute a circle, it will be a circle in 2D. Here it will be a point, and here it will be a sphere. It will be a 3D sphere. So it will be a sphere. So it is a sphere, third order. So S will be some number into sigma hat axis plus some number into J omega D wali axis plus some number into Z hat wali axis. Just like in a complex notation I'm writing, because it is not possible to write here in 2D, so I'm just writing in 3D. So understand, it will be a 3D plot like this. Into Z hat like this. It will be a 3D plot. So again, here sigma is greater than 0. It will be a 3D plot. So using this equation, you will get basically no identity, because similarly in the first case we just saw what is identity, sigma greater than 0. That will make no contribution. Already we know that sigma is greater than 0, so nothing it will make. Then we'll see the steady state error. What is KDC? It will be limit S tends to 0, d of s into g of s. Now see here, d of s into g of s already has a s here, and if you put a 0 it will be infinite. So it will be infinite, this again is infinite. So ESS is 1 by 1 plus KDC, that is 0. So irrespective of the order of the system, PI controller always gives 0 steady state error. This is one observation. So that's why PI controller is preferred over P controller. So here also you won't get any identity to tune KP and KI. Then comes the transients. Transients again same. I'll just copy paste here. Similarly, about this also I'll just copy paste. Rise time, settling time, and peak overshoot. These are the things. Now, in this case, or here I'll just write sigma. So here it will be omega n less than equals to 1.8 by tr. This will be the radii of the 3D circle, maximum radius of the 3D circle, sphere, not circle, 3D sphere. This limitation, and this limitation, that is sigma less than equals to 4.6 by ts, or basically the negative of it defines a plane, because sigma contains the information of the both the axes in this. So to visualize, I'll just see how to visualize it, and solving this using the above analysis. Here we'll get minus theta max less than equals to theta less than equals to theta max. So here this theta will be the 3D angle projected. It will be the 3D angle or the solid angle, which will be difficult to visualize. So I'll just quickly draw like how will be the possible orientation of the parameters. This is sigma axis, say this is j omega axis. I'll just like hat, this doesn't make any sense, but this is just to show like this. So what is the equation number 1? Means equation 1 is the stability, there is no identity. Steady state also there is no identity, because already steady state is 0, so there is nothing you can get. Then yeah, all the identities are in terms of the transients only, rise time and this and this. So first is on the maximum radius of the 3D sphere. So I'll draw 3D sphere. Like this will be the 3D sphere. This will be the radii omega n, that is 1.8 by tr. Our identity says that it has to be inside it, so I'll just write like this. Inside the 3D sphere. Like this, first identity. This is second, and this is third identity. So this is first identity. Second is nothing but a plane. So just like in the first case, we'll find a in case this is the plane, like this, somewhat like this. and this will be what? Sigma equals to minus 4.6 by Ts. So it has to be inside it, this side of the plane, using equation number 2. And obviously sigma greater than 0 means this, there is one more plane here. This plane is sigma equals to 0. And this is another plane. This pink one is the minus 4.6 by Ts plane. So our this thing will be between this thing, sigma range. Between these two planes our sigma will be there, and inside this sphere. Then comes the 3D angle. Again it will be a conical structure like this. I'll draw it like this. From here, like this. This is the theta. It has to be inside it. Then what will be the overlapping area? This will be the overlapping area. So between the planes, like this, will be the area. What do we call it earlier? Region of controller design. This is the region of controller design. This is just a visualization. Now we can find the Kp and Ki. So basically from this, what is known as K sigma omega n is known. Then using this identity we can find theta like that. Both we can write minus zeta max less than equals to zeta less than equals to zeta max. The zeta expression will be same for both the cases because it doesn't change. So equation 3 we can modify and we can write as this. Okay, sorry, not this. Yeah. So zeta, using these three equation you can tune your controller in such a way that all the things lie in this area. So this is how you can do the controller design using the time domain analysis. Now if you see, if the order of the system increases, it is very difficult to visualize using the complex plane, and very difficult to tune the parameters, because we have to formulate a lot number of equation and we have to satisfy each and every equation. That's why time domain analysis is not suitable for higher order equation. So we go for frequency domain analysis. So in frequency domain analysis, we need to have any of the two parameter of the system, and the order of the system can be any order. So we should know either the bandwidth of the system or crossover frequency and the gain margin or phase margin. Using only 2-3 things, we can find the KPK values very simple using algebraic equation. If it is a pair controller, we should need 2 equation and we will be in a position to solve it. So frequency domain analysis is very simple to design the controller. Frequency domain analysis, there are different types of frequency domain analysis. One is called as pole zero plot and another is called as the loop shaping analysis. So the frequency domain controller design we'll see in the next lecture. Thank you.